4 crores. He has published about 130 technical papers in various national and international journals and conferences. He is an active reviewer of many international journals. So we are very fortunate to have you, sir. I welcome you for your expert speech. Please, sir.
So thank you very much for your introduction. And now I'll be sharing my screen, sir.
Okay, sir.
So my PPT visible.
Yes, sir.
Okay. So I'll start. So good afternoon, one and all. So this is Dr. Panduranga Vandavalli, Professor in the School of Mechanical Sciences, IIT Bhubaneshwar. So I am going to give talk on Biped Robotics and its gait generation using soft computing. Just a moment. So these are the contents of my presentation, overview of my presentation, introduction, the problem definition, and a model of 7 degrees of freedom biped robot, Day's parameter setting, the kinematic relationships, dynamics, the results of analytical method that we proposed, and the results of subcomputing methods that we developed, and finally the robustness test of the algorithms what we proposed. So before actually entering into this presentation, I would like to brief the vocabulary which we use during this presentation. So coming to the introduction, a robotics structure that resembles the shape of human being and capable of walking with the help of two legs and exhibit the characteristics very similar to the human walk is called a humanoid robot or biped robot. The name itself implies that it is a biped having two legs and its structure is very much similar to the human beings. And it is also having other part depending upon the requirement for the robot. We may include the legs, arms, and the head, the torso, depending upon the requirement, various parts can be added so that it will be exhibiting characteristics more similar to the human being. It is also called anthropomorphic robot, which can exhibit motions, characteristics very much similar to the human beings. These humanoid robots are developed by various research groups around the world to study and simulate the body structure and its behavior. So in the early days, that was the main objective of the groups working in the field of humanoid robots around the world. And the initial aim of humanoid research was to build better orthoses and prostheses for the human beings. So initially it started like a branch, so that can design various limbs like orthoses and prostheses that can fit to that will be suited uh, to a particular human being. So when they met accident or when they lost certain limb of the body. So that was initially it was started and like that, and so later on it was resulted in the development of mechanisms and structures similar to human being. So then that study related to the design, development, and fabrication of such structures is called humanoid robotics or biped robotics. The study was popular in that name. And if you observe this animation, like how that biped robot execute motion or walking, so that is called executing the gates. So when the robot is moving from one location to another location, the various parts of the legs will be moving in one particular fashion. So that is called the gait. Okay, similar to the human beings walk, the gait cycle, the gait cycle of the biped robot also consists of two phases. So when we walk, when the humans walk, so our walk consists of two different phases: the single support phase and double support phase. As we can observe this in this animation. So most of the time, So we are going to during a gait, the human beings are going to spend most of the time in the single support phase, and the double support phase is almost instantaneous. The purpose of this double support phase is to just exchange the leg support, exchange the leg support. And when we are working, or the robot is working with the help of two legs, so balancing the gait is the tough job. Similar to human beings walk, the biped robot walk also need to be balanced. So the balance of the robot is to be measured with the help of two different criterion. So this was used by many of the researchers all around the world. So that is static balance and dynamic balance as mentioned here. So the walk need to be balanced, either statically balanced or dynamically balanced. Now we are going to see actually what is static balance and dynamic balance. So static balance is attributed with very slow walking. The static balance is attributed with very slow working, and the robot is said to be statically balanced as long as the center of mass of the system is falling inside the put support polygon. So whenever we walk with the help of our 2 foot, so then if you are standing on single leg, the support area under the single leg is meant to be your foot support polygon, and when you are in double support phase, so the entire region will be your foot support polygon, that we will see. So when you are there in single support phase, only the support leg area will be treated as the foot support polygon. When the robot or the humans are there in double support phase, the entire area that is so like this. So this entire polygon is considered to be our foot support polygon. As I said, static balance is attributed with very slow working, but the robot is expected to perform the work at a desired speed in order to perform the task. So therefore, for the biped robot, static balance is not so important. So we have to consider dynamic balance. Why? Because the robot is to execute the task that is assigned to it in a predefined amount of time. So therefore, the dynamic balance is utmost important. So how to define this dynamic balance, or the dynamic balance of a robot? So the robot is said to be dynamically balanced as long as the zero moment point is falling inside the foot support point. So in the earlier case, so when the robot is said to be statically balanced, so we are going to talk about the center of mass of the system. Center of mass of the entire system, the working mechanism should be focused either in the single foot support polygon or in the double support phase foot support polygon. So then we can call that the robot is statically balanced. Means the work is attributed by very slow working. But coming to the dynamic balance, so a new term has been introduced, that is zero moment point, that is called ZMP. So if you wanted to say that the robot is said to be dynamically balanced, then we are focusing about a point that is called the zero moment point, and the zero moment point should fall inside that put support point. So how are you going to define the zero moment point? Now the next definition says GW is a point in the foot ground interaction plane, and is defined as the point about which the moments generated by various links of the biped robot are equal to zero. Yeah, when the robot is moving, or when the human body is moving, so when it is moving, the links are about to generate movement about an axis. So in this case, this zero moment point is a point so about which the moments generated by all the links are equal to zero. So that point is like located on the foot ground interaction plane. So now if you observe this diagram, here we could see this is the single support phase, this is the leg extension of the leg, and this is the point where the ZMP is acting. ZMP means zero moment point about on the foot support polygon or the foot ground interaction surface. This point is acting, and about this point, all the moments generated by various links will be equal to zero. That is called the zero moment point. So by knowing zero moment point alone, so we won't be able to describe the dynamic balance of the robot. If you know the location of ZMP, and that is inside the foot support polygon, then we will be able to say that the robot is said to be dynamically balanced. But what is the extent of balance? So how much the Biped robot is having what stability? So that is called the extent of balance of this biped walking machine is determined by using another parameter called the dynamic balance margin, which is also called dB. So what is this dynamic balance margin and how we are going to define this? So once you know the zero moment point, that is the point about which all the moments generated by uh, various links of the robot is zero. So now if you want to define dynamic balance margin, it is the distance between the point where ZMP is acting and the end of put support polygon. It is the distance between the point where ZMP is acting, this one, and this is the end of the put support polygon. So this distance is called dynamic balance margin. If the ZMP is acting at the center of the foot, like whenever we are standing still, we are not moving. So then, at that case, what is going to happen? Your ZMP is supposed to fall at the middle of the foot support polygon. Means the robot is having the maximum balance. So when you are walking, and what is going to happen? The body is moving one direction in the forward direction, and the ZMP is also supposed to move in the direction of motion. So when it is moving like slowly, it is moving, and up to certain extent only this motion should be allowed. If it is crossing beyond this foot support polygon, what is going to happen? The ZMP is leaving the foot support polygon. As a result, the biped robot or the human being is going to lose the balance and it is going to topple. So then what we are doing? So when this situation happens to us, when we are walking on a slippery surface, or when you suddenly place your foot on the peel of a banana, what is going to happen? The friction between the foot support polygon, the foot and the ground, that is at the surface, is not sufficient, and it will be started skidding. So what is going to happen? Skidding means the ZMP is quickly trying to move out of the foot support polygon. So then we feel that we will be losing balance. So that time what we will be doing, just we will be making some motion, that is giving some action, swinging our hands in the opposite direction of our fall and trying to generate moments in the opposite direction of fall. So that what we are doing, so we are trying to pull the ZMP back once again inside the foot support polygon and trying to stabilize. So I'm trying to balance ourselves. So that is how this mechanism works. Here in this case also. So when the ZMP is just moving out of the support polygon because of the motion, aggressive motion of the robot, so then what we have to do in order to bring it back to once again inside the foot support polygon. So we will be once again making or generating movements in the opposite direction by moving the hands in the opposite direction, so that the uh, point will be balanced and will be brought back to inside the foot support polygon, and the robot is said to be balanced. Okay, this is how this mechanism works. So the ZMP is moving very close to the end of the foot support polygon. The same thing, it means that the biped robot is losing motion. So our objective is to try to keep the position of ZMP close to the center of the foot, so that the balance of the robot is maximum, so we can avoid fall of the robot. So these are various terminology or vocabulary that we are going to use continuously the rest of this talk. Okay, we're going to talk about gates, we're going to talk about single support phase, double support phase, static balance, dynamic balance, zero moment point, and dynamic balance margin. Okay, so based on those terms, we will be able to assess or establish the gate and assess the performance of the gate. Okay, so now I am going to describe a problem related to the ascending and descending gate generation of a 7 degrees of freedom biped robot moving on a staircase. So just I am trying to give information about a 7 degrees of freedom biped robot. This is the minimum possible degrees of freedom with which we will be able to construct a biped robot. So beyond that also we can by increasing the degrees of freedom also by providing hands, by providing more degrees of freedom legs to the legs, we may achieve this biped robot configuration. Later on we have also solved that configuration, but in order to have the ease in establishing the gates and to explain the various characteristics of the biped locomotion, at minimum 7 degrees of freedom is required. So therefore, I'm taking the help of 7 degrees of freedom biped robot and we try to solve the problem of gate generation for this biped robot when it is ascending the staircase and descending the staircase with the help of an analytical method and then with the help of subcomputing based method, and we'll see how they are performed. So this schematic shows a 7 degrees of freedom biped robot that is moving on the staircase. If you observe, there are lines. Now I am tracing those lines. This represents our staircase. Okay, and so there are some thick lines that represent the structure of the biped robot. Once again, I'm trying to trace. This is 1 foot, and this is the lower limb of one leg, swing leg. This is the upper limb of the swing leg. This is the upper limb of the stance leg, and this is the lower limb of the stance leg. This is another foot, and this is the trunk of the biped robot. So altogether there are 7 links, and these links are joined to each other with the help of 1 degree of freedom and establishing 7 degrees of freedom biped robot. If you observe here, this is 1 degree of freedom at the foot, and this is at the knee. Like there are 4 degrees of freedom link for leg one and leg two, 4 degrees of freedom, and at the hip we are having 3 degrees of freedom. Like that, if you see, this is one leg, and this is another leg, and this is sorry. This is the trunk. Okay, so this is 1 degree of freedom and this is another degree of freedom, this is another degree of freedom. So this is the side view, and here so we are having 3 degrees of freedom established at the hip, two for joining legs to the hip and one for the hip joint trunk that is to be joined to the hip. Okay, so then if you observe this diagram closely, there are link lengths L1 to L7 is established, and there are masses. If more importantly, if you see, there are the mass of the link, corresponding link is assumed to be focused at a particular location on the link. So this type of system is called lumped mass system. Instead of using a particular leg having continuously varying distribution of mass, which will be difficult to analyze or to go for integration continuously, and which will be computationally expensive. So therefore, what we did, so we decided to go with a lumped mass system. So in which the entire mass corresponding to the particular link is assumed to be focused at a particular point. So that is called lumped mass system. That is M1, M2, M3, M4, M5, M6, M7 are placed at R1, R2, R3, R4, R5, R6, R7 on the links L1, L2, L3, L4, L5, L6, and L7. So this is the architecture of the 7 degrees of freedom biped robot. The the important limitation so with this structure is that this structure can move only in one direction. So that is in the direction of motion. If it is set to move in this direction, it can move like this only. It cannot take any turn because we have restricted the degrees of freedom. If you could provide more degrees of freedom at the hip here, two degrees of freedom at the connection of both the legs, then the robot will be able to take a turn. But in this case, our objective is to demonstrate how we'll be able to generate gates means the sequence of steps involved when the robot is moving on the staircase. Therefore, we limited our degrees of freedom to only one at the joining of the leg to the hip, so that the entire mechanism will be moving only in the direction of motion. So, which is sufficient for us to analyze the characteristics of this gate. So another important thing is that there is a curve which is shown like this, which is called the swing foot trajectory. Even when we walk on the floor or on the staircase or in an uneven terrain, our swing foot always, whenever we are lifting our foot and trying to place it location, so always we carefully see whether there is something lying on the floor. If something is lying on the floor, we try to lift our foot so that it is not going to collide with the object or the stool or whatever that is placed on the ground on the terrain. And once again, we'll be carefully placing our foot on the floor so that there is no slipping occurs. So here in this case also, when the biped robot is moving from one location to another location, as it is a machine, we have to define the motion for the swing flow. So therefore, in this study, so we decided uh, to provide a cubic polynomial trajectory for the swing foot. The swing foot is assumed to follow a cubic polynomial trajectory from the start to the goal, so that it will be completing one gate cycle. So that is also shown here, and in the enlarged view here, if you observe, so what is happening, what is the position of ZMP, yeah, where is it located, and how are you going to decide the dynamic balance margin? All these things are given. In addition to that, we have also given the conditions for the structure of the terrain. What could be the width of the stair, and what could be the height of the stair? Okay, all these things are explained in this figure. So when we walk, or when the biped robot walk, which is exhibiting characteristics which are very much similar to the human walk, the location of the hip, this one, the location of the hip with respect to the position of the foot placement. This is the position of the stance leg, and this is the position of the about to swing leg. So when the robot is uh, located on the staircase, we are having, this is the location of hip joint, this is the location of stance leg, and this is the location of would be swing leg, location of the center point of would be swing leg. So during this bipedal walk, these 3 points are going to make an important what do you call characteristic. Like this hip joint is always going to make some relationship with this the center point of these legs, stance leg and would be swing leg. Like the parameters shown, that is high H1, the height of the hip from the center of the swing foot or would be swing foot, or L1, that is the horizontal distance of the hip joint. So from the center point of would be swing leg. And similarly H2, the height of the hip joint with respect to the stance leg, and L2, that is the horizontal distance of the stance leg with respect to the hip joint. So these four parameters play a major role in establishing the inverse kinematics for the system. So these are all links. They are going to establish certain relationship. If this point is moving, why? Because this will become my swing leg. When it is moving, this position is moving, because if it is moving, the height of the hip joint and the length of the hip joint from this location is varying. As a result, the inclination will be varying. Say for example, at this particular joint, the link may be like this. So by utilizing these 2 points, two parameters H1 and L1, and by following the trigonometric approach, so we will be able to establish the gait for the lower limbs. Limbs means below the hip joint. So that is the included angle made by the lower portion of the leg, upper portion of the leg, that is swing leg, the upper portion of the leg and lower portion of the stance. So these four parameters or these four variation in joint angles can be obtained so with respect to the height and the distance of hip joint, so from the center point of the particular leg. So this is how we establish the gait for lower limbs in one cycle. And coming to the other, that we will discuss later. So once again, here if somebody is having some touch with robotics and kinematics, they will be able to understand. So what is the purpose of these parameters? I think there are two scientists called Dinawat and Attenberg who established a procedure that will be used to establish the forward kinematic solution for any manipulator configuration. So these parameters are very much essential to determine the kinematics and the dynamic behavior. Dynamic behavior, what is the equation of motion and what is the torque required at each and every joint in order to execute the desired gait. So for that, these parameter setting is very much essential. We have also established the these parameters for this robotic configuration at various joints, and we have extracted the days parameters. Alpha is the twist of a link, A is the length of a link, theta is joint angle, Di is the joint offset. Okay, so these are that is the meaning of the four parameters, and these are the values for the given robotic configuration. So as we have used all rotary joints, theta remains only joint angle and Q1 to Q7, and all these are zero. So now once again coming back to how we established the gate for the biped robot while working on the staircase, the, the the first and foremost important thing is to establish the foot trajectory. Like whenever we walk, we start walking. The first and foremost thing that we did, we plan the trajectory or the motion for our swing leg. Similarly, here also we have to just decide what could be the trajectory followed by the swing foot. So, as I already mentioned in the earlier slides, that we have considered a cubic polynomial trajectory for the swing foot. So, what does it mean? Cubic polynomial means this is the representation of a cubic polynomial that we have seen in our regression equations. Z is equal to C0 plus C1x plus C2x square plus C3 x cube, where C0, C1, C2, and C3 are the coefficients of this cubic polynomial. So, in order to obtain the x and z, here in this case, if you observe this diagram, we have considered that this coefficient is x and z. This motion is x, and the vertical perpendicular to this x is considered as z. So when the moment we define this trajectory, we need to establish the coordinates in terms of x and z. So that's why we have written this equation as z is equal to in terms of constant and the values in x. So as there are four unknowns in the cubic polynomial, there are four unknowns like C0, C1, C2, and C3. We have to solve these four unknowns by establishing the boundary conditions. So therefore, to solve that, we have established four boundary conditions in terms of the terrain conditions and the parameters of the robot. Here you observe in this, SW represents the width of the stair, SH represents height of the stair, FS represents length of the foot support, and X1 and Z are the coordinates, the Cartesian coordinates. So with the help of these four coefficients, we will be able to obtain four simultaneous equations, and solving those equations, you will get C0, the values for C0, C1, C2, and C3. Then if you know the location of x from a certain reference point, then you will be able to define what could be your z, so that you will be getting that cubic polynomial trajectory in x and z. Okay, so then once you establish that, then as I mentioned earlier, so we have used the inverse kinematics approach to determine the gates for the lower limbs. Gate for the lower limbs means there are these are called lower limbs. The limbs below the hip joint is called lower limbs, and the angles associated with are this with theta 2, theta 3, and this one theta 4. This is theta 5, theta 6, and theta 7. Theta 1, theta 2, theta 3, except theta 4, theta 5, theta 6, theta 7. These six are associated with the uh, lower body or lower portion of this biped robot. And from these six, as I mentioned, theta 2, theta 3, theta 5, theta 6 can be determined with the help of H1 and L1 and H2 and L2. And the variation for this foot, the support foot is where it's parallel to the ground and it has taken the shape of the ground. So it's theta 7 is 0. And now we left with there are two unknowns, theta 1 and theta 4. So we left with two unknowns. Those are theta 1 and theta 4 need to be uh, identified. So which is not that easy. So if it is a one variable, we can manage. There are two variables. Either we have to go for inverse dynamics approach or semi-inverse method. So which is computationally very expensive. So what we tried, we thought of removing this expensive method and to obtain a forward method of establishing that we have developed some process that I will be explaining. See, before explaining that, I will once again come back to the determining the gates theta 2 and theta 3. You have to remember the numbers carefully. Theta 2 and theta 3 are the gates related to the lower link and upper link of the swing leg. So, but by knowing H1 and L1. So, these are H1 and L1 of the hip joint, the height and the length of the hip joint from the swing foot. By using those parameters and with the help of the link lengths L2 and L3, the length of the lower leg and upper leg of the biped robot, we have calculated theta 2 as well as theta 3. The similar procedure and for the stance leg also by using H2 and L2, and we will be able to calculate theta 6 and theta 5. So with this, we could calculate theta 2, theta 3, theta 5, and theta 6. As I already mentioned, theta 1, theta 7, and theta 4 are left. Theta 7 is 0 because it is oriented along the terrain. And coming to the theta 1 and theta 4, as we have to use computationally expensive semi-inverse method or inverse dynamics approach, we thought of simplifying the problem and assumed the variation, no assume no variation for the swing leg. So instead of sometimes whenever we're working, we swing our foot like this and lift and land the foot with certain angle to the ground. So here to have once again simplicity in computational complexity. So we assumed a flat footing, which is having certain drawbacks, but even though compared to the drawbacks that we are going to obtain, the ease in computational complexity or the reduced computational complexity forced us to prefer no variation for the swing. So then we left with only one trunk variation, that is theta 4 variation. So that we have followed a particular methodology, that is, so determine the trunk motion for the half cycle after considering the static balance for the robot. The beginning I said, the static balance means we are going to balance the center of mass, and the center of mass should fall inside the foot support polygon. Here, what we did, we have given some motion for the trajectory for the center of motion. Based on that, we derived theta 4. And then what happened? We have obtained theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, theta 7. Variation for all the gate for all the links. So now we verify. As I mentioned earlier, for the biped robot, dynamic balance is more important than static balance. Even though we obtained the variation for the trunk using static balance, that gate is verified for its dynamic balance. If it is found to be balanced, means the ZMP is falling inside the foot support polygon, then only it is said to that the robot is said to maintain the dynamic balance, otherwise not. So if it is so, then After the half of the cycle, then we are trying to follow the repeatability conditions which are mentioned here. If you observe the motion of the human being, so when we start from one gate and by the end of the gate of the particular cycle, simply simply the gate variation of swing leg will be shifted to stance leg, and stance leg will be shifted to swing leg. That is called the repeatability condition. Now by doing so, what we are doing, we will be ready for the next walking cycle, so without any difficulty or without any break. So therefore, once you complete the half of the cycle, for the rest half of the cycle, we should ensure that the links will be following repeatability conditions by exchanging the gate. So that we did it, and once again we have verified for the dynamic balance of the gate. And once it is satisfied, then it will be supplied to the robot for executing or for moving from one location to another location. So as I said, once the gate is done and ready, now we have to verify the gate for its dynamic balance. As I said, dynamic balance, it cannot be measured directly, and it has to be measured by measuring the location of the zero moment point of the generated gate. So what is that zero moment point? It is the point about which the the moments generated by various links or limbs of the robot are, uh, are made equal to zero at a particular point. So if this point is located on the foot ground interaction surface, so it is that point we are going to determine, so about which all the moments are zero. So here I said there is XZMP. Similarly, as the beginning I mentioned, it is a 7 degrees of freedom system, and which will be moving in only one direction, that is in the direction of motion. So therefore, we will be getting variation only in x direction. If if your robot is taking turn, if you by increasing the degrees of freedom, then what is going to happen? The moment of the masses are also present in y direction. So therefore, there is a variation in ZMP occurs in y direction also. So in that case, we have to calculate YZMP also. So as we restricted the motion of the robot in only one direction, so we have calculated only one variation in X ZMP, and then we decided what is the dynamic balance margin. Half of the put support polygon minus point where ZMP is acting will give you the dynamic balance margin in X direction. So with that, we will be able to identify whether the generated gate is dynamically balanced or not. So now we are interested in finding the dynamics. That is nothing but deriving the equation of motion. Deriving equation of motion involves that determining what is the torque required to move a joint from one location to the another location. That is the target location. That we have to determine. So based on that, we have to select our activators, and that will perform the task. So for that, in this work, we have used Lagrange Euler formula, which is a popular dynamics based approach, dynamics approach for determining the equation of motion for the robotic system. So this is the equation that determines LE formulation d by dt of dou L by dou Qi dot minus dou L by dou Qi is equal to tau by. Tau by means this is the torque required to move a particular joint by some angle. So here a thing is L, which is called the Lagrangian or Lagrangian function. So which is nothing but the difference of kinetic energy and potential energy. So we will be establishing the equation, and then from that we will be solving those equation, and we will obtain tau 1 to tau 7, what is the torque required for at each and every joint of the biped robot when it is moving from one location to another location. So here, this is the final form of the equation. Those who are in multi-body dynamics or in the field of robotics, they will be able to identify what is this equation. This is the final form of the equation of motion. It is obtained by using Lagrange Euler formulation. That is tau I is equal to that concept dik, that is inertia term. HIKM called Coriolis the centrifugal term, and CI is the gravity term. And each and every term is having their own expanded form. Okay. So with this, we will be able to identify what is the torque required. And once you obtain the torque, and we are also interested in what is the power consumed. So power required is obtained by averaging the power over a cyclic time period of time t. So with this, we derived the gait and verified the dynamic balance and obtained the equation of motion and finally calculated what is the power required. So then we also attempted to derive the gate for descending the staircase. So here, ascending and descending gates of the biped robot in differs in only two ways. That is establishing the trajectory conditions, and the second one is moving the robot in the direction of gravity. So in the earlier case, when the robot was climbing or ascending the staircase, it was moving against the direction of gravity, and when it is moving or moving downwards or descending the stairs, it is moving in the direction of gravity. And once again, here when the robot is moving or descending the stairs, the boundary conditions also differ. Ascending, it is having one type of boundary condition, and while coming, it is also following different conditions to solve to solve the coefficients of cubic polynomial of the swing foot trajectory of the robot while descending. So once you obtain the formulation for SN or analytical method to solve the gates for biped robot when it is ascending and descending the staircase, the performance of this algorithm is evaluated in computer simulations by pro- providing assuming certain parameters for different limbs of the biped robot. As I said, there are seven links, and each link is having their own mass, their length, the position of the mass, and the important parameter moment of inertia of each link. And with that, if you run the program, and we have got the data as shown in the table here. So the dynamic balance for ascending the gate is seen to be 0.020831 meters, and the power consumed is 47.37 watts. Similar descending dBm and power. If you observe the ascending and descending motion of this biped robot on the stairs, we got the results like the balance of the robot while ascending the staircase is seen to be little higher than descending. And once again, the power consumption, the robot is found to consume more power and more power while ascending the staircase than descending. So these two facts, like balance, having more balance and consuming more power, and less or during ascending, and less power and less balance during descending, or fall in line with the behavior or with the experience of human beings. Like we also, when we climb the stack, we feel like we are more balanced than when coming down the stairs, and we also feel like we exhausted our energy while climbing the stair when compared with descending. So these two observations are falling in line with the experience of human beings, and so we observed that the analytical method we developed is also uh, giving better result by observing this phenomena. So this is the gate. If you observe while ascending and descending, so we have got gate, but because of the fact, as I mentioned, that in order to determine the trunk motion, we have used the static balance. Maybe there is a variation in deciding the trajectory of the center of mass during static balance. Because of that reason, so there is slightly mm, a different gate which we are not going to encounter in our daily life, staircase ascending and descending. So there is the reason. So we will now uh, going to the next approach, that is subcomputing based approach. So it was very powerful tool that can handle uh, imprecision, uncertainty, and partial truth. So whenever we deal with the robots, so most of the time we try to collect the information from the sensors. All the time the sensors are not going to provide you exact and accurate information. So there is uncertainty that we will be getting some wrong information, and wrong matlab there is some uh, incorrectness in the data. So even though with that imprecision and incorrectness in the data, how the robot will be able to take a decision? So for that, to accommodate the robot in taking a right decision, so we are going to develop algorithm uh, that can take that uncertainty into picture and solve the problem. So here we tried to utilize two different algorithms, neural networks and fuzzy logic to model the gate generation problem of the biped robot and optimize these structures, like neural network and fuzzy logic, with the help of genetic algorithm. So, when compared to your previous approach, where a huge amount of mathematics was used to derive that analytical method, so that problem has been simplified, and here we are not going to use the exact mathematical formulation of the problem. So, with the help of this neural network and fuzzy like that is the advantage. The complex mathematics will be eliminated, and we try to simplify the problem and try to take care of the uncertainties that are arised from the sensors and other environments. So coming to this neural network, we all know nowadays in the form of earlier these tools were popular in the name of subcomputing, and now same tool with slight modifications are more popular in a different name. That is artificial intelligence, machine learning, okay, and deep learning. So these are the names. So the same principle that I am going to explain. So if you observe, this is the structure of a multi-layer feed-forward neural network. Here, if you observe, neural network consists of different layers, and the first and last layer are called input layer and output layer, respectively. And in between, we may have multiple layers. Those layers are called hidden layers. So there is a method. So in deciding the number of hidden layers that are being required in order to model the problem. So nowadays, whatever the machine learning based models and deep learning based models will be having more than one hidden layer that is to retain the information related to the system. And earlier we were using only one hidden layer to reduce the computational complexity. That time also people tried. In the last 15 years, people tried whenever required. They were also increasing the number of hidden layers. But ultimately, the introduction of new hidden layer uh, is going to cause the enhanced complexity in the computations. Therefore, in this study, we restricted ourselves to only one hidden layer, and there are neurons present in each and every layer. So the neurons present in the input layer are called input neurons, and the neurons present in the output layer are called output neurons. The number of neurons present in the input layer and the number of neurons present in the output layer are determined by the number of inputs and outputs of the system. But there is a method to, once again, you have to follow an approach or a systematic method to determine what could be the number of neurons in the hidden layer. So, which ultimately decides the architecture of the network. So, in addition to the number of neurons, we also need to decide. So, there are values called V11, V21, and W11, W12, like that. Vij and Wjk. Those are called weights. Vij represents the weight that connects the input layer to the hidden layer, and Wjk represents the weights that connects uh, the hidden layer to the output layer. So finally, if you decide what could be the number of neurons present in the hidden layer, and what could be the connection weights for these uh, connections between the neurons, that decides the architecture of this network. Okay. Now this slide shows the forward calculation. We have used only feed-forward neural network that is optimized with the help of genetic algorithm. Actually, normally this uh, feed-forward neural network will be coming up with backpropagation algorithm. We all know that the backpropagation algorithm is a traditional optimization method which starts with the help of uh, a single solution generated at random. But we all know that the solution may get stuck in the local optimal solution. So that's why here we thought of optimizing that neural network with the help of genetic algorithm. So therefore, I have explained only one pass, that is forward calculation. So once again, while doing this calculation, we have considered linear transfer function for the input, and log sigmoid for the hidden layer, and tan sigmoid for the output layer. That is the transfer functions that are used to establish the mapping between uh, input and uh, output data at various levels. So if you use only a linear mapping, a linear transfer function at the input layer, so whatever the output you are calculating is equal to the input. Okay, if you observe here, as there is only linear mapping, whatever the input I am providing, I will be getting the output. So now what could be given as input to the neurons present in the hidden layer? So that is the weighted sum of all the inputs or all the output. Weighted sum of all the outputs from this neurons will be given as input to a neuron in the hidden layer. So that's why I'm saying weighted means there are connection weights between the particular neuron in the input layer and hidden layer Vij and I. If Vij is seen to be 0 means the, the output is not having any weightage. If it is 1, we will be taking complete weightage of the output, complete we will be giving complete weightage to the particular output while in transferring that input to the next layer. So like that, the weighted sum of all the inputs will be given as input to the hidden layer here. Then by following log sigmoid transfer function, we will be transforming the signal to the output layer. That is 1 by 1 plus e power minus a1 and hij, that is log sigmoid. And then whatever the outputs that are obtained, once again there is a w, the weighted sum of all the weights, the weighted sum of all the outputs of the hidden layer will be given as input to the neurons present in the output layer. Once again we calculate the weighted sum of all the outputs of the neurons present in the hidden layer, and then by passing it through this is tan sigmoid transfer function. As I mentioned, the output is we are having tan sigmoid transfer function at the output, so that will be transformed by using this formula. So with this we have got OK, which is called the calculated output. So now we are having TOK. So when these neural networks are, we are giving training to the neural networks, there are two types of learning or training: supervised training or supervised learning, or unsupervised training or learning. Supervised training means there is you will be having both inputs and outputs, so that the network will be mapping between these two. So there is a target to be achieved, that is called supervisor. So that's why it is called supervisor learning. We are having labeled data in the case of supervisor learning. In the case of unsupervised learning, there is no target. With the help of the outputs that are being obtained from the network, we will be constructing one objective function and we will be optimizing that objective function. By that, we will be tuning the network. So now as we have given the target also to the network and we have calculated the actual output, now we are going to compare these two. So that is called the error signal. Okay. So this error signal in the case of back propagation algorithm, this error signal will be propagated back inside the network to adjust the weight values. So in this case, as we are using genetic algorithm, there is no need to update the weights. So we will be, so in the case of genetic algorithm and the non-traditional optimization methods, so we will be starting our search with the help of multiple solutions. So therefore, no need to update these weights. Every time we'll be getting new weights that are a population that will be stored as weights, and the updated and the optimal weights will be coming every time. So in the evolve through the genetic algorithm. So therefore, we'll be stopping at the calculation of error, so that we will be going to the next population, and like that we'll be optimizing the network with the help of genetic algorithm. So the next thing is that fuzzy logic based approach. Here in this case we have constructed both neural network based gate planner and fuzzy logic based gate planner. So coming to the fuzzy logic, it was based on fuzzy theory, and which is uh, universal set, fuzzy set, nothing but the universal set. So which is having values between 0 and 1. Whereas in the case of ordinary set theory, we will be having values either 0 or 1. So this works like in between also we will be having values. This fuzzy logic controller, when executing, it consists of four different modules. These are rule base, and inference engine, fuzzification, and defuzzification. So the entire calculations in fuzzy logic, they are going to be operated on fuzzified data. Fuzzified data means they are not the numericals; they are represented with the help of linguistic terms. The whole processing happens in the fuzzified form with the help of inference engine and with the help of rule base, and we will be getting once again fuzzy. Before here we will be having fuzzified output. Fuzzified output means once again it is in the form of linguistic term. But if you see that linguistic term, so we won't be able to interpret properly. So therefore, to have proper meaning and to obtain proper control action, that fuzzified output need to be defuzzified, and that will be used to control the process. So this is how a fuzzy logic controller is going to work. And coming to this and then so for both neural network, optimizing the structure of neural network and optimizing the knowledge base of fuzzy logic controller, if you see these two tools, neural network and fuzzy logic, both of them they work based on uh, the operation of human brain, but there is slight difference. This neural network works based on how human brain gets training from our childhood days till death. So here what we will be doing, we will be given with some inputs every time and some outputs, and the brain will be mapping, and it is getting trained. And the performance of this network also depends upon how much amount of data that we will be providing to train the network. So therefore, the neural networks are called data-driven systems. Coming to the fuzzy logic, it also works on the principle on which brain works, but it works a slightly different way. It works like how human brain takes decision. So whenever we are walking on a road, when some vehicle is coming in front of you, and then how our brain makes calculation and takes a decision so that we successfully avoid the collision. So there is some calculation happens, there is some knowledge present in the brain, so with the help of which it is capable of taking a decision. So that's why this fuzzy logic is called knowledge-driven system, consists of knowledge base, which once again consists of database and rule base. So the success of the fuzzy logic controller always depends on how effectively we design the database and rule base of the fuzzy logic controller. So therefore, the designer of the fuzzy logic controller should have an idea on the domain knowledge. Whereas in the case of neural network, the designer of the neural network need not know anything about the physics of the system. So that's why people generally say neural network works like a black box. Whereas coming to the fuzzy logic, the designer, because as I said, it is having certain knowledge about the process based on which it is taking a decision. So therefore, the success of the fuzzy logic controller purely depends upon how the designer designs the database and rule base of the system. If somebody is not knowing about the system, if he designs fuzzy logic controller, it may not be effective. But whereas if the same person designs fuzzy logic control after providing some training with the help of known data, it will be able to converge or provide some meaningful prediction. Okay, now our objective is once you design a neural network or fuzzy logic controller, how these two things can be tuned with the help of genetic algorithm. So therefore, we will be able to have an optimal neural network and fuzzy logic models that can establish uh, a gate that can establish that can provide a gate for the biped robot when it is ascending and descending the staircase. So here also just I try to uh, give to some information on how the genetic algorithm works. As I mentioned, genetic algorithm is a non-traditional based optimization algorithm, and it starts with the help of a group of initially initial guess solutions generated randomly. Initial solutions generated randomly. Whereas all traditional methods, they start their search with the help of only one initial guess solution. But here all non-traditional optimization methods like genetic algorithm, particle zone optimization, differential evolution, artificial equality, teacher learning based optimization, uh, all these algorithms, they start their search with the help of initially generated group of solutions. So therefore, the possibility of not stucking the solution in the local minima is less. Here, always we will be saying that the solution that we obtained is near optimal or optimal like that. But whereas in the case of traditional, we say that the solution may get stuck in the local optimum. Here it is generated, we are going to generate some initial populations, and population nothing but the problem variables that will be generated, and we will be having objective function in the optimization. These values will be substituted in the function and we will be getting the functional values. That is also called the fitness of the population, which shows the worthiness of the solution that can be carried to the next generation. So then here in the case of genetic algorithm, we are going to follow a termination criteria, that is the number of generations. Initially, that is at the first generation, the condition is not fulfilled, no, and it will be going to uh, this genetic operators. These are called reproduction, that is also called parent selection, crossover, and mutation. So during this process, the best population from the initial population will be selected, and a mating pool will be formed. The parents will be selected, crossover happening. Crossover means there is an exchange of properties between the parents. That is called the crossover, and then mutation happens. By the end of the mutation, we will be having a modified set of population, and that concludes a generation of GA. Then it will be going to the next generation, and like that it will be continued to number of generations. And when the termination criteria is reached, then we will be stopping the execution of the program, and we will be providing the best population. So that is in this case the best population may corresponds to best neural network, or the best neural network architecture, or best fuzzy logic controller configuration. That is the best knowledge base, that is the best database and rule base. That is our objective here. So once you know uh, the operation of these three methodologies, that is neural network, fuzzy logic controller, and genetic algorithm, and now we try to hybridize these algorithms so that the best out of these algorithms can be taken, uh, and we will be getting um, best gate planner. So that is the objective. So here our aim is to go for GNN, means genetic algorithm trained neural network, and genetic algorithm trained fuzzy logic controller. Here in both the cases, irrespective of GNN or GFLC, in both the cases we have used two modules. This is the first module and this is the second module. The purpose of this neural network or fuzzy logic controller is the same. Whatever the parameters we are giving input, whatever the parameters that we are considering as output are the same for both the modules. The only difference is, so in the case of GANN, the purpose of GA is to optimize the weights of the neural network, whereas in the case of GFLC, optimize the knowledge base of the fuzzy logic controller using the genetic algorithm. So the purpose is same for genetic algorithm in both the modules. But coming to the first module, what are the input? That is x1 and x2 are considered as the input. That is nothing but the position of foot placements of the robot on the staircase. And by using that, so we are going to calculate the height and the distance, height and L. H1 and L1 and H2 and L2 will be calculated as outputs are predicted from the network, and with the help of which H1 and L1, as I already mentioned, we will be calculating theta 2, theta 3, theta 5, theta 6. So from that we will be calculating delta theta 2 and delta theta 3, and by using that, so earlier delta theta 1 assumed to be 0, and in this case, as I said, that time we will have to use either semi-inverse method or inverse dynamics method to calculate two unknowns. So therefore delta 1 theta 1 was made 0, means that is flat footing, and only theta 4 was calculated from the static balance, and the entire gate was verified for its dynamic balance. So here in this case, delta theta 7, but because it is once again based on terrain condition that we have not considered, but we have incorporated delta theta 1 and delta theta 4. So without including the computational complexity or the mathematical formulation required to establish uh, the semi-inverse method or inverse dynamics approach. And after that we have calculated the torque and the gates. And if you see, this is the structure of or architecture of neural network uh, to solve the problem. As I mentioned, it is having x1 and x2 as the inputs and h1 and l1 as the output, with the help of which we are calculating theta 2 and theta 3. And in a step, and for the next step, we will be calculating delta theta, the change in the value of delta theta 2 and delta theta 3, and they were given as input to the network, and we will be getting delta theta 1 and delta theta 4 as the outputs. So these are the various functions use linear activation, tan sigmoid and log sigmoid for different layers of this network. And as we have used binary coded genetic algorithm, the architecture of this neural network is represented with the help of binary digits. So that weights and the bias values of the neural network are represented with the help of ones and zeros. Okay. And this is how one string of GANN is represented with the help of the bits. And as I mentioned earlier, so you are having a network. So the inputs and outputs are fixed. And what could be the number of neurons present in the hidden layer of both the modules of the network? So for that, a systematic study is conducted and obtained 5 and 3. So while ascending, the neural network is found to have 5 neurons in the first module of the neural network in the hidden layer, and 3 neurons in the hidden layer of the second module of the neural network. And for each variable that we are using 5 bits to represent, and finally one population is represented with the help of 340 bits while ascending the staircase. Similarly, while descending also we have conducted some study and obtained 4 and 3 number of hidden neurons in the first and second module of the neural network, and found to have 280 bits. And so this is how the fitness of one GS string. As I said, once we have the GA string, its fitness is calculated by substituting the values in the function, and we'll be getting the fitness values. So here the string means it is a neural network. So, so this is how we are going to calculate the fitness of each string, and as the string represents the motion of the biped robot, and overall we are trying to find the dynamic balance margin, which shows the stability of the dynamic balance of the robot when it is working on the terrain. So that way we have formulated the fitness function for this problem. And similarly, as I mentioned, in both the cases, fuzzy logic and neural network, we have used two modules, and the inputs and outputs remain same for both the modules. Okay, same. And here, this is a representation of database. I said the the operation of fuzzy logic controller is purely dependent on the knowledge base. Once again, consists of database and rule base. So this is the representation of database. Here, the database is represented in the form of membership function distributions. Somebody is having some idea about fuzzy logic, and otherwise it is a big topic. So, so these are called membership function distributions. And in this problem, so we are trying to represent this database with the help of triangular membership functions, and each membership function is represented with four linguistic terms. These are L, M, H, P, H. So these linguistic terms, while explaining the operation of a logic controller, I said all the information will be processed in the form of fuzzified information. Even though you have some real number, that real number needs to be converted into a fuzzified form with the help of this membership function distribution and linguistic terms, and the data will be processed in the fuzzified form, and you will be getting fuzzified output, which that you could not have meaningful information. That needs to be converted into defuzzified output, means that is a numerical value with certain magnitude that may tell you how the control action will be taking place for the particular system. So this is how both for first module and the second module of the neural network, how we are going to constitute uh, the database in the form of membership function distribution and linguistic terms. And I said the other important part is the rule base, formation of the rule base. So for forming the rule base, we are trying to use the if then else conditions. So that is if x1 is low, x2 is m. These are the linguistic terms. And then what is going to happen to the value of h1 and m. Similarly for the second module also, and this is how we are going to represent a string of fuzzy logic controller uh, with the help of genetic algorithm. So here we are using genetic algorithm to evolve the fuzzy logic controller automatically, and it is also called auto FLC. It is automatic evolution of fuzzy logic controller with the help of genetic algorithm. So why we are calling it as automatic evaluation? Earlier I said the designer of the fuzzy logic controller should have the knowledge of the domain. Otherwise, it is very difficult to establish the database and the rule base. So now, by utilizing GA, even though if someone is not having any idea over the domain, so he will be able to use fuzzy logic controller by assigning the entire task of designing the database and rule base to the genetic algorithm. So that's what is called automatic evolution of fuzzy logic controller. And once both the algorithms are developed, GANN and GFS algorithms, that will be used to like ascending and descending the staircase. So it has been tested. The dynamic, the table shows the dynamic balance margin values in meters. The length of the foot is 0.6 meters, 0.06, and 60 centimeters. and on one side it is 30 centimeters. We're trying to maximize, means we're trying to push the ZMP towards the center so that the maximum value could be 30. If I finally push the ZMP towards the center, it could give measurement of 30 centimeters, but 30 millimeters, sorry, 30 millimeters, but it has come to be 0.02526, like that, 0.027, trying to maximize the balance. This is for ascending, and here also the 10 test cases for descending. So in both the cases we have got uh, the gates are dynamically balanced. And if you see the variation earlier, if you observe the analytical approach, uh, the posture of the trunk, it seemed to be little awkward, bending backwards in both ascending and descending. So that time I said this might have happened due to the selection of wrong trajectory for the swing for the center of mass while determining the trunk motion. So, but here what we did, so here we have given the task completely to the genetic algorithm to design the best structure of genetic algorithm to evolve the best knowledge base for the fuzzy logic controller, and you could see that it has developed uh, reasonably uh, fair gates. If you see this, we also feel that we will be slightly bending forward and backward, not that much that what we have got during analytical approach. And these two approaches say that the gate generated is well within the required variation, and it has also executed a smooth variation from one step to another step in both ascending and descending cases. And finally, we also conducted some robustness tests, as I already mentioned. So, as this robot, we are trying to make it as an autonomous system. So, it will be collecting inputs from various sensors and trying to process that data, and accordingly tries to activate the activators. And in that process, if there is uh, a problem in the data that we are collecting, uh, there is huge noise. Most of the time, whatever the data we will be collecting, that needs to be filtered and apply filtering and try to reduce the noise. And sometimes the noise levels are high over long usage of the sensors, and that time the your gate planner will be getting a huge variation in the inputs, that is foot placements. So then that time how this gate planner will be reacting, whether it will be able to provide a feasible gate to the robot or not. For that we have conducted this robustness test by varying the inputs between plus or minus 15%. And finally we could see there is a maximum of minus 2.0 minus 2.12% change in the dynamic balance margin of this the entire gate generated. So with this we could also conclude that the gate planners, GNN and GFLs based gate planners seem to be robust in nature and can provide the gate for the biped robot while ascending and descending the staircase. And these are some of the robotic developments at IT Bhubaneshwar, as Professor read during my introduction. We have almost there is one robot. This is a wall climbing robot. Than that, we have got two patents, and there are 15 working robots we developed at IT Bhubaneshwar, and we mostly focus on the biologically inspired robots and the development of exoskeletons or human assisted devices and the building of intelligent machines. So these are various. Let me see. Increase that now. Okay. So these are various. Then we have also developed this one. This is a pipe inspection robot. This is the robot is need to move in a 5 centimeter diameter pipe, for inspection of the boiler tubes, and it can go forward and come backward, and it can go with the help of camera with the light, so that it could also see the condition of pipe inside. This is one CPRS sponsored project, and this one is active exoskeleton, mm, which will help the paralyzed people to move from one location to another. This is a DST based project, and this is one passive exoskeleton that will be used to uh, support the soldiers when they are carrying around 30-40 kilo weight during their travel from one location to another location. So there will be a backpack, and they will be keeping the items here, and the load will be transferred directly to the ground. So this is one DRDO based project. Like, we are working on human assistive devices and others. Thank you. Open for queries.
Thank you very much for such an elaborate presentation, sir, on biped robotics and soft computing. Now, I would like to ask the participants to please raise your hand for asking questions. Or you can also post your queries on the Q&A section.
Any doubts? And not only this topic, overall robotics, artificial intelligence, the
Ashu
combined.
Singh is there, sir. Please allow him to talk.
Yeah, sure. Yeah, Mr. Ashu Singh, please ask your question. You can unmute yourself. Mr. Ashu Singh, are you able to hear?
Hello, am I audible, sir?
Yes,
Yes,
yes.
yes, please. Please ask your
Okay,
question.
sir. Actually, I have only one simple question. You were saying that can you get the slides, sir?
Answer. Can you tell me? You ask. You can. No problem. You ask.
Okay, right. So you told that we have assumed one equation, that is tan sigmoid equation,
That is the transfer function. Transfer function. Yes.
transfer function. So
Hmm.
you told that, sir. We actually you assumed that tan sigmoid function. That assumption was based on what, sir?
No, no, no.
Sometimes.
There are, yeah, there I mentioned there are three transfer functions. There is one linear transfer function, one log sigmoid, and tan sigmoid. So just I have used like that. Now you need to experiment for each
Okay,
layer.
okay,
Either you can go
okay.
with the linear, tan sigmoid, long sigmoid, like that. You have to
Right, sir.
conduct
Right, sir.
some
I,
experiment.
okay. Thank you, sir. I got my answer. Thank you.
Thank
Thank you, Mr. Ashu. Anybody else? Any other questions? Please raise your hand. Yeah, Mr. Faisal.
Hello.
Yeah.
I'd like to ask one question.
नहीं नहीं समझ में आता assumption डाला हैं
Have
Yes,
you
please
Yes.
tried
Yes.
continue.
using reinforcement learning?
Pardon.
Have you tried using reinforcement learning for bipedal robots?
No. We have not used reinforcement.
So how does it? Is it going to be better as compared to the other two approaches that you mentioned?
So we have you actually when you are using it for biped robot applications. So far, the entire training and learning is offline. So we were not having the fresh coming information. So when the moment when you use reinforcement, whatever the data that you will be coming, that you can feed like that. So that closed loop is not there. The entire training was done offline only.
Yeah, but there are environments like
Yes,
gym
yes,
or
you can,
Simulink.
you can. We have not tried so far.
Okay, thank you.
Yeah. Next question, please. Mr. Anbarasu KG. Yeah, please. Please unmute yourself. Anbarasu.
I think no question from his side.
Sir, just wanted to ask one question. What are the main challenges in designing the biped robot, sir?
The first thing is that balance is the major challenge. The
Yeah.
balance, and now so many robots are available. Now people are started doing. So only thing you should have proper foot size. We have to decide what, because whatever the imbalance we have, if you want to design a robot, if you have slightly bigger foot, then most of the balancing problems can be solved. This is one way of approaching. Otherwise, it is very difficult. We faced a lot of trouble in designing my first robot. Really, we struggled balancing in millimeters, so that it is very difficult to bring it back to the what do you call that ZMP inside the foot support polygon. After struggling a lot, then one idea came to me that okay, why don't we increase the weight, because we are the designers and we have to ensure that the robot should not lose the balance in any case. Okay, balancing is the main. Further, the important thing: design the foot carefully and little oversized so that it will never lose the balance.
Okay. Okay. Thank you, sir.
Thank you.
Sir, sir.
Namaskar.
Yes, thank you so much, sir, for accepting our invitation for your nice presentation also. We are hoping for your next lecture in near future, sir. Your
Physical this
presentation.
time. This time we'll plan for physical meeting. Like
Yes,
that.
Yes,
sir,
definitely,
sure.
sir. We want to call you in the physical mode, sir.
Sir, actually, I want to share that we have already applied for the Atal FDP in
Ah,
physical
ah, ah.
mode, and
Yeah.
you are one of the speaker on that, sir.
No, nice, nice, nice.
Yes, sir. Surely
Physically, I
we'll
want to
invite you.
see university.
Yes, sir. We will surely invite you, sir.
Yeah,
Thank
all
you.
the
Thank you, sir.
participants are. Yeah.
Yeah.
Sir, one more.
Ambedkar ji, namaskar, namaskar.
Thank you,
Thank
sir.
you.
Thank you very much.
Namaskar, sir.
All the participants are requested to please fill the feedback form, which will be shared soon in the group. Thank you.
Thank you,
Thank you,
sir.
sir. Thank you, sir.
Yes, we can close the meeting, sir.
Sure.